All right, so we're going to be talking about why electromagnetic waves refract. All right, so why do electromagnetic waves refract? All right, so let me just draw two types of medium. All right, so let's just say that this is air, this is water, and this is air. And supposing that the light ray is going at an angle, what is the normal? The normal is always 90 degrees to the surface. So this is the surface. So it's 90 degrees. So this is the normal. That is 90 degrees to the surface. Now, if there was no water, the light ray would just go in a straight line. However, because it bends towards the normal, so let me just do this dotted line. So this dotted line. So this dotted line shows what would have happened if there was no water. However, because it goes in a denser material, so this is denser, it will go towards the normal. So the arrow is going this direction, this direction. Now let's just say that this is air. So again, you draw the normal to where it hits the surface. So this is the normal. Now when it comes out of the water and it goes back into air, it will travel parallel to its original path. So it would be like so. So it would come out like this. All right, so this is what happens. So the light ray hits the surface at an angle. So let's just say this is θ1, and the angle is always between the normal and the ray. So here would be θ2, and this would be θ1. Okay, so because the light ray goes through a denser material, it would bend towards the normal. So bend towards the normal. And this dotted line is if there's no water. If there's no water, that path would go in that direction. However, because it goes through water, it will bend towards the normal, so it would go in this direction. When it comes out of the water, goes back into air, it will travel in the same direction as before. All right, so why does it do this? Right, so we need to look at the atomic level. So this is the atomic level. So here you've got protons in the nucleus and neutrons, and you've got electrons. Now you've got a light ray going in. Now what happens is that this light ray will interact with the electrons. Now generally, if you didn't talk about at the atomic level, because light interacts with matter, it just slows down. So it interacts with matter, and so therefore it slows down. Alright, so if you want to have another explanation, there are three explanations. So the first one is Fermat's principle. Of least time. Another one is absorption. Let me explain absorption. So what happens is that this light ray, it interacts with the matter. As it interacts with the electron goes down to an energy level. So let's just say these are energy levels. So it interacts with the electron goes down. So this is an arrow, it goes down an energy level. So when it goes down an energy level, it emits the light. Okay, so the original electromagnetic wave, it hits the electron goes down an energy level, and then it re-emits light. So the electron goes down, it re-emits light, and then that light hits this one, let's just say, and it happens again, and it re-emits light. So because it's constantly absorbing light, constantly re-emitting light, it takes time, so it's longer. So it takes longer. If it takes longer, therefore the average speed is slower. The average speed is slower. By the way, when it goes through a different material, the frequency doesn't change. So the frequency does not change. Okay, so the frequency does not change. Alright, so that is one explanation for absorption. Now the third one is that when the electromagnetic waves, once it hits the electron, now what happens is that the electron will oscillate. The electron will oscillate. What happens when the electron oscillates? So the electromagnetic waves, it goes in, it hits the electron will then oscillate, and then it produces another electric field. So it produces another electric field. So that stands for electric. I'll put an arrow at the top because it is a vector. Now what is an EM wave? An EM wave stands for electromagnetic, doesn't it? Electromagnetic. So EM wave stands for electromagnetic. It has an electric field and it has a magnetic field. And I'm just going to call that E arrow and B. So E stands for electric, B stands for magnetic. So what happens when the electromagnetic waves, what happens when it hits the electron will oscillate. It then produces another electromagnetic field or electric field. And then what happens is that it adds the original wave. So it adds, or it's a superposition. So it produces another electromagnetic field. It adds to the original wave, adds to original, and another wave is created. So another wave is created, and that is why you have this wave rather than the original wave. And once it passes through the water, because now there's no interaction with extra matter, it carries on as before, and that is parallel to this. All right, so now another reason why I put the angles there is because I'm going to talk about Snell's law. I think it was originally described by Ibn Sal, Persian scientist. Okay, so what Snell's law says is that n1 sine theta 1 is equal to n2 sine theta 2. And what is n1? Now n1 is the refractive index. And n is equal to c divided by v. Now normally the refractive index is bigger than 1, so n is bigger or equal to 1. So what happens when c is the speed of light, and v is the speed of the light in that medium. So speed of light in a different medium. Alright, so when v is equal to c, you get n is equal to 1. So that is for a vacuum. Yeah? Alright, so the refractive index tells you the property of the material. That tells you the speed of light in that material. So that is the refractive index. N1 is the refractive index. Theta 1 is the angle between the normal and the ray. So here would be theta 1 and here would be theta 2.